let's continue. So you remember in the last class we studied these free fermions with these psi operators, psi of z, and their OP was given by psi of z, psi bar of, let's say, z prime is equal to 1 over z minus z prime. Similarly, psi bar of z, psi of z prime was 1 over z minus z prime. These two are the same because z minus z prime is odd under switch, and psi and psi bar pick up a minus sign under switch. Okay, remember psi and psi bar were both, we were looking at the theory of the C equals 1 fermionic theory, a theory of 2 fermionic fields, or 1 complex fermionic field. Okay, psi and psi bar were both left moving, there are corresponding right moving guys. Okay, and we studied last time this theory in the NS sector. You remember what that meant? It meant that when we were in the cylinder, we had these fermions and we put anti-periodic boundary conditions so that we expanded the fermion momenta and half integral. The fermion momenta were demanded to be half integers. Okay, so that was what, and in the NS sector, we understood the state operator map. As you remember, the identity operator was the vacuum, was equal to the vacuum. And you remember that alpha minus half corresponded to psi, state psi. And then del psi was alpha minus 3 by 2 wedged to del psi, and so on. Right? You increase the number of derivatives, and that increases the weight of this alpha operator. And products of psi's went to products of these alphas. Right? So the state operator map in the NS sector was very simple. Okay. We also discussed at the end of the last class that the theory that modular invariance would fall. So modular invariance is just statement that the theory on a torus, when put on a torus, is genuinely diffeomorphically invariant. You can choose any cycle you like as your basis cycles. Invariant under both small and large diffeomorphisms. Okay, so modular invariance would force us to consider another sector in the theory. This Ramond sector, the sector in which fermions were not just were periodic around the circle. And at the end of the last class, we sort of ended with a bit of a puzzle. And the puzzle was this. We understood this state operator map a bit too well, in the sense that we exhausted the spectrum in the NS sector with a set of all operators we could easily write down. So all polynomials of size and their derivatives were in one-to-one correspondence with the operators in the NS sector. But now if we're going to introduce this Ramond sector, a new sector, like a new winding state sector, that kind of thing, the new sector, we would need new operators, but all the polynomials in psi and their derivatives have been used up. So what are the operators corresponding to this guy? Okay, so we're going to try to answer this question in this lecture. Luckily, there is a way of constructing these operators in an explicit way. Sometimes operators in a quantum field theory are only constructed implicitly. An operator has insertion in a path integral, which is local, which affects the path integral only locally. Then. And sometimes you cannot do better than by specifying an operator by saying, an operator is a location where fields have a certain discontinuity, or there's a certain winding or a certain flux or something emerging out of fields. This is a common thing in the study of quantum field theory. For instance, monopole operators in 2+1 dimensions. That's how we specify them. Okay? And that's fine, and if needed, we can work with that definition. Do you understand? It's specifying a certain specified singular configuration of fields at a particular point can often be a good specification of an operator. And that's sort of what we'd have to do if we worked in the purely fermionic language. But in this particular case, it's possible to give a more explicit description of these Ramond sector operators using this lovely trick of Bosonization, which is of great interest in its own right. So that's the route we're going to take. Okay.
You use the word small gauge transformation, large gauge transformation.
Yes.
Can you recall the
Okay. So a small gauge transformation for me at this point, in different contexts you use those words differently. For me here, a small diffeomorphism is one that is continuously connected to identity. Okay, a large diffeomorphism in this context is one that is not continuously connected to identity. Just that.
So inversion will be one kind of.
Inversion would be a sort of large thing in dimensions where it cannot be reached. Yeah. Right. But the large ones here were simply taking the diffeomorphism that takes you from this choice of cycles on the torus to this choice of cycles on the torus. Okay. So yeah, you cannot go continuously to it on the same torus. You can go in the space of tori, but that's going to a different manifold. On the same torus, this is just a discrete thing. Is this clear? Yeah. Okay, excellent. So, in order to, please.
So, this is kind of a diffeomorphism.
Yes.
So, and diffeomorphism in context of gravity is like gauge transformation.
Yes.
So, when we have some kind of gauge transformation, we can associate some conserved quantity. So, is there a different kind of, will there be a corresponding conserved quantity?
For large gauge diffeomorphisms? No. You see, even in the context of, well, at least there's no conserved, you mean this conserved currents come from continuous kinds of things. And the conserved current corresponding to diffeomorphisms, of course, is the stress tensor, right? As we've seen on many occasions. Now, you're asking, you see, first one has to be careful. It's true that symmetries are associated with conserved things. Gauge invariances are associated with currents in the sense of, okay, let's take one or two steps back. First, it's important whether the gauge symmetry we're considering is actually gauged or not. So had we been coupling this theory to gravity, then these diffeomorphisms would actually have been gauged. Okay? Of course, we're not coupling the theory to gravity. We're just saying that, look, the quantum field theory on two manifolds that are the same but just written in different coordinates should give us the same partition function. Okay? That would be a consistency requirement if we coupled to gravity, because otherwise it would break diffeomorphism invariance and give junk. Right? You can't break a gauge symmetry. Okay? So this is, however, in the current context, it's a sort of aesthetic requirement we're placing on the field theory. Okay? There's nothing really wrong with studying a field theory that makes sense in flat space, but has odd properties on the torus. We're just demanding that these theories be good. It will be needed for various other things we do. Okay? Now, I raised this point for the following reason. Gauge symmetries and global symmetries are just different things. Okay? Gauge symmetries don't necessarily come with conserved quantities. For instance, in QCD, okay, any confining gauge theory, we have this huge gauge invariance, but since it's confining, there is no part of that gauge symmetry that becomes a global symmetry. Okay? So QCD is not associated with any global symmetry, the gauge part of it. On the other hand, QED is. Okay? Electron charge is conserved. Charge is conserved. Okay? Because there is a part of this gauge invariance that acts non-trivially on the theory that survives at infinity. So, so the question of whether gauge symmetry is associated with a conserved charge or not is, there's no yes, no answer to that. It's a case-by-case thing. Okay? On the other hand, global symmetries usually are associated with these conserved charges. Now, after all this broad blah, 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 you were asking, is there, regarding this diffeomorphisms as a global symmetry, because that's what we're doing. Okay, is there a conserved current associated with the yes, it's a stress tensor. Is there a conserved something associated with these discrete things? In some sense, yes. Let me give you an example. One of these discrete guys is tau goes to tau plus 1. Okay? So remember that our partition function was trace q to the pi L naught q bar to the pi L naught bar. remember that q was equal to e to the power 2 pi I L naught and 2 pi I tau, and similarly with q bar. Okay, under tau goes to tau plus 1, tau bar also goes to tau bar plus 1. Okay, so we tau bar goes to tau bar plus 1, but q bar has a minus sign because of the I here. Okay, so under tau goes to tau plus 1, what are we shifting this guy by? We're shifting it by e to the power 2 pi I L naught minus L naught bar. So if you demand that your partition function is invariant under this transformation, it must be that e to the power 2 pi I L naught minus L naught bar acts trivially on the spectrum. But what does that mean? L naught minus L naught bar is spin. So it tells you that your spin, all spin quantum numbers have to be integers. Okay? So in that way, you forbid angular momentum being half integer. Now this is forbid angular momentum being like square root 2. This is a sort of obvious thing, but it comes out of this. So in some sense there are consequences like this. The modular invariance acting on the partition function has enormous consequences for the spectrum. So in some sense you can regard that as a consequence of a symmetry. Okay, yeah. Good. Other questions or comments? Excellent. So let's keep going. So this is one of these half classes, right? This board doesn't go up and down, but this one. Okay, excellent. So what we're going to try to do is to try to understand this fermionic theory in bosonic language. So I'm going to have to give you one more reminder before we continue. And the reminder was of our study of compact bosons. It was just 3-4 lectures ago, but we have these lectures so rarely that you've probably forgotten. So, so let me remind you. You remember that we had these lovely formula. PL was equal to n by r plus minus omega r by alpha prime. So PLR was equal to, that was the plus minus. N was the number of momentum units. W was the number of winding units. Our compact boson had radius r. And with these formulas, we had L0 is equal to alpha prime by 4 PL squared. L0 bar was equal to alpha prime by 4 PR squared. Okay? All this was for the study of a bosonic theory that had whose correlation functions were x of z, x of 0 were minus alpha prime by 2 log of z bar. Okay? Now, if you look at all these formulas, especially this formula, you see that there is a convenient choice of alpha prime to make to simplify the formula. And that convenient choice is alpha prime equals 2. Okay? So sometimes when we are dealing with a theory that has nothing to do potentially with strings moving in space-time, okay, we will just set alpha prime equals 2. Okay? So I'll rewrite these formulae here at alpha prime equals 2. So we get PLR equals n by r plus minus omega by 2r. L0 is equal to PL squared by 2. L0 bar is equal to PR squared by 2. And we had x of z, x of 0 goes like minus log z minus log z bar. Yeah. Alpha prime is the context of string state. So, yeah, it's just, we worked with an action that was 1 by 4 pi. Okay. We worked with an action that was 1 by 4 pi alpha prime d2x del mu x del mu x. Okay? Yeah, it's a field redefinition. Oh, equivalently in these new coordinates, I think it's good to distinguish the guys that have alpha prime in those. Let's call these guys H. So it's just working with the action 1 by 8 pi d2x del mu h del mu h. Okay? It's just, as you say, absorbing into x and h. That's the redefinition. Okay. Now, look at this theory at r equals 1. Okay. Remember, alpha prime was set equals 2, so that's r equals half of alpha prime. Okay, so if we were keeping alpha prime, we're looking at this theory at r is equal to alpha prime by 2. Equivalently, you could look at it at r is equal to, r should have been measured in units of square root alpha prime. So it's equivalently, it's looking at it at r equals, this is in the secretly r is equal to 2 square root alpha prime. R was 2, half square root alpha. Half square root alpha prime, but of course same as 2 square root alpha prime by t duality. Remember, r and alpha prime by r are the same theory. Okay, so whether I say half or 2, it's just whether I look at momentum or winding. Okay? If we look at this theory at r is equal to 1, okay, or if you kept the alpha primes, this is what it would be. Our spectrum here becomes n plus minus w by 2. This is PL. What? R is 1. Yes. Okay? And what? Suppose we looked at the operators e to the pi PL x. Then these operators have scaling dimension PL squared by 2. Okay? And PL squared by 2, okay, so let's take the value of PL equals, n is equal to 1, w is equal to 0. Okay? In that case, PL squared by 1, so n is equal to 1, w equals 0, we get is equal to half. Okay? So we have operators in our theory with dimensions half, and we will have many other operators we will, because this is a free boson, on top of half we will have all integers over it, because you can take, apart from these sectors, you can take any number of del x's that you want. So you'll have half, 3 halves, so on. Okay? So this theory here, okay, this theory here has a spectrum that has some features that are reminiscent of the spectrum of the free fermion. What? All this will come together with the right moving ones. Yeah, at the moment we're not talking about the right movers at all, but when we look at the modular invariant partition function, they will be crucial. Okay? But right now we're focusing on the left movers. Okay? In particular, the mode with n equals 1, so the mode with PL equals half, has exactly the same spectrum, has exactly the same scaling dimension as the free fermion. Okay. Now you could ask, was this just a coincidence, or is it something deeper? Okay. So we're going to try to suggest n equals 1, omega equals 0, or equivalently PL is equal to 1. This mode what we're groping towards is that this theory will end up being the same as the theory of 2 free fermions. And under that equivalence, this mode will turn out to be the operator psi. Okay? So we're groping towards that. So this mode is going to be in correspondence with the operator psi. We want to check whether this is just some vague coincidence or there's something more to it. So let's look at it in a little more detail. Okay. First thing we note is the following: psi of z. Okay. Also, there is the mode with n is equal to -1 and w is equal to 0. This mode we're going to put in correspondence with psi bar. It's another field with dimension half. Okay, and in the fermionic theory, we had both psi and psi bar with said dimension half. Okay. Now we're going to look at this a little more carefully. See, you remember this OP, psi of z with psi of 0. This went like order z. First, it didn't have a singular term. Also, it didn't have a constant piece in its OP, because the constant piece, if it had existed, would have been psi of 0 squared, which is 0, because psi is a fermionic field. Okay? On the other hand, psi of z with psi bar of 0 went like 1 by z. That was this thing here. Okay? Let's compare this to what we see from these e to the power h's. So let's look at e to the power ih of z, e to the power ih of 0. So remember, of course, all these, though I don't write it usually, these are all normal ordered operators. And to compute this OP, we use this Baker-Campbell-Hausdorff, this Wick formula that we wrote down in class, this contraction formula with the exponential. Okay? And of course, there's an easy way to remember the answer. The way I remember this for these exponentials is not by actually looking at those derivatives and so on. The way to remember it, at least the way I remember it, goes as follows. I imagine Taylor expanding it. And we have h of z, and then there is plus blah, blah, blah. We've got an e to the power I1 plus ih of 0 plus blah, blah, blah. And then the first contraction we would get in this Taylor expansion is contraction of h with h bar. But we know that what we're going to get is e to the power something times correlator of e to the power ih of 0, normal order e to the power h of z, e to the power h of 0. We know we're going to get something like this. So what could that something be? Well, its first term is going to be this 2-point function. So it's going to be exponential of that 2-point function. Of course, you should work it out properly, but this is a way to remember, to get the signs and so on right. Okay, so what do we get here? What was the 2-point function? H of z with h of 0 was log z. Okay, there were two factors of I. H of z with h of 0 was minus log z. Okay, we had minus alpha prime by 2 log z. So you get minus log z, and we have two factors of I. So that gives you minus 1. So we get e to the power log z times this, times normal order this. Is this clear? But e to the power log z is of course just z. So we get order z, in fact not just order z, we get z times normal order e to the power I h of z, e to the power I h of 0. It's not, when we're looking at this as part of a full vertex operator. The vertex operator involves both left movers and right movers. And you remember we have checked when we studied the compact boson that full vertex operator was single valued. Okay? Yes. So we're looking at the left moving part, but there's also a right moving part. When you put it all together, there's no multi-valued. This is actually part of a genuine theory. Actually studying these multi-valued operators has its own interest. It's the study of what people call vertex operators. And it makes contact with another very beautiful branch of physics, namely the study of Chern-Simon's theory in 2 + 1 dimensions. And that's something we will get to in the course. But at the moment we're studying legal theories. Single valued theories, single valued operators. No, though parts of the operator may be multi-valued. But when you put them all together, everything is single valued. Okay? Excellent. So the first thing we see is that we get z. Okay? In agreement with what we would have expected here. We'll come back to expanding this a little more. In fact, let me just expand it for a minute now. Okay, so when we do this, suppose we take z equals, z is equal to as we take z to 0, we just expand this in Taylor expansion. So it's e to the power 2ih of 0, and then into 1 plus del h plus I del h, blah, blah, blah. Right? The rule, as always, is within normal order, you can treat operators like numbers and Taylor expand at will. Okay, so that's what I've done. For now, all we care about is that we get z times something. As we go on in this class, we will care about the details of what we could. Okay, excellent. Is this clear? Now let's also do the other computation. Suppose I do e to the power I h of z times e to the power minus I h of 0. Well, the computation is the same, except we've got an extra minus sign. Okay, so we will get e to the power minus log z times normal ordered e to the power I h of z e to the power minus I h of 0. And so we'll get 1 over z and then 1 plus I del h plus blah blah blah. Is this clear? Okay. So the first thing we see is this, that psi of z, psi bar of 0 had 1 over z plus stuff. We get exactly the same singularity with exactly the same residue. Okay? And the second thing we see is that psi of z, psi of 0 had psi of z, psi of 0 had a 0, and this guy also has a 0. Remember, psi and psi bar had the same weights as e to the power h and e to the power h bar, which of course is part of what we've already said, otherwise they couldn't have had the same singularities. Okay? So these theories seem very, very close. Can we do even better? Can we take the statement from seem very close to a clear statement? Okay. Let us now compute. Suppose I was just back in the fermionic theory, and I was computing psi of z1, psi of z2, psi of zn, psi bar of w1, psi bar of w2, psi bar of wn, m. Actually, because of un, because of the invariance under this, I haven't even told you this. Maybe let me say it in words now and we'll establish it as well. The fermionic theory has a U1 global symmetry. That U1 global symmetry just was phasing of psi and reverse phasing of psi bar. You see that this is a symmetry just from the Lagrangian, which was psi bar del bar psi. So you phase psi by a constant, you phase psi bar with by the reverse constant symmetry of the theory. Okay, you could ask what was the current for this U1 global symmetry? Well, the current is the thing that that clicks when you've got a psi bar. It gives it charge 1, okay, or charge minus 1. So depending on your definitions, it's either psi bar or psi bar psi, depending on which one you want to be positive and which one you want to be negative. So psi bar of z is the U1 current of this fermionic theory. Okay, let's do a sanity check. Currents have to have dimension 1. Why do currents have to have dimension 1, somebody? The integral of the current is a conserved charge, so it's dimension 0. And we're in 1 plus 1 dimensions, so the integral is over a 1 dimension manifold. Okay, currents have to have dimension 1, but this clearly has dimension 1 because this, by the way, is normal ordered. Because normal ordered psi bar picks up the dimension of psi plus dimension of psi bar. The fact that it's so simple is related to the fact that it's a free theory. Operators, their dimensions just add because the theory is free. If you don't believe me, you can check by computing the OP with the stress tensor. You just get twice the singular terms, right? Contractions with psi plus contractions with psi. Okay, excellent. So this theory has this conserved U1 symmetry. So all correlation functions will vanish in this theory unless there are as many psis as psi bars. Right? A correlation function vanishes unless the total charge under any conserved current is 0. Why? Well, what? Because of the symmetry of the theory. You should get the same correlation function if you perform the symmetry operation. But perform the symmetry operation is rotating the psis and reverse rotating the psi bars. But you pick up a net phase if the number of psis and psi bars is not the same. So if it was not the same, you get the number is not the same, you get the equation. Whatever the answer is equal to the same answer times phase rotated. And that's a contradiction unless the answer is 0. Right? So this theory will have only correlation functions only when number of psi's is equal to number of psi bars. Okay, so this is the most general correlation function we can study with insertions of only psi's and psi bars. Okay, great. So let's study this correlation function. Once we know the answer to this, we can take as many derivatives as you want. Right? I've given you what the path integral is with these insertions. Now, what does it mean? What does the correlation function with path integrals with derivatives mean? It means path integral at this point minus path integral at this point divided by epsilon. So there's no new information. That's the point, right? Derivatives are just linear combinations of known operators. So once you have this, you've not lost any information by not keeping derivatives. Right? Excellent. So let's work this out. Now, you might think we're going to have to do a heroic job of Wick contractions to work this out. And you can take that route if you like. It's fine. However, there's a very easy way to get the answer. And the very easy way to get the answer is to notice that this function has to be analytic everywhere except when z's meet w's. Moreover, when z's meet w's, there has to be a pole. Right? So if we write down the singularity structure of this answer, it has to have a term which is like, so let's call these guys i's and these guys m's. So I, product over I and m, z 1 over zi minus wm. There has to be this factor in the answer. Because every time any z meets any w, there's a pole. Now there's something else we know about this answer. And that something else is that when any two of these signs come together, the answer vanishes. There's a simple 0. That was, well, I didn't write it down here, but that was this statement that psi of z, psi of 0 is like O of z or order z. In fact, we can do better. What is this z? Z del psi is psi of 0. Because since there's no singularity, you can just Taylor explain. Plus blah, blah, blah. Right? Okay. So then we see that there must also be a factor I less than j, zi minus zj. But the same argument holds for w's. So now there must also be a factor m less than n. Okay, you forgive that there are two i's are the same here. Okay, let's g less than k. We'll run out of symbols. Alpha less than beta. Okay, correlation has to, a function has to take this form. And then whatever else it has to have no singularities and no zeros. Okay. Moreover, what can we say about the behavior of this function at infinity? At infinity, okay, or equivalent, yeah, at infinity, the totals, at infinity or just scaling, the total weight of the right hand side in z's, in 1 over z's, has to be 2m times half, has to be 2m times half, because we've got 2m operators, each of dimension half inserted. So the whole operator under scaling, the whole correlation function under scaling, has to scale like 1 over z to the power m, 1 over distance to the power m. Okay, so that tells you that the homogeneity of this answer has to be 1 over distance to the power m. Okay, but now let's do some counting. What was the homogeneity of this guy? Well, that was minus m square. What about this guy? Okay, this guy with this guy meet, together make all the cancel all the off diagonal guys here. I and m. This was I less than k, but there's another alpha less than beta. So all the off diagonal guys are cancelled. What's left is only the diagonal guys, which are here because these were different things, but not here. So you see that if you do the counting, you will get that the mismatch is that the denominator has m more terms than the numerator. I mean, we can write down the formulas, but it's easier to just see it, right? Okay, so this formula here has scaling dimension. The right hand side is scaling dimension like 1 over distance to the power n, which is exactly as what we wanted. Okay, so if there is a final answer, there's an additional piece in the answer. It has to be completely analytic. So if I have, so the answer has to have these factors, can multiply another piece. Whatever that is has to be completely analytic. Has to have homogeneity 0. Okay, but there are no such functions. All functions that are everywhere analytic in the complex plane, bounded and infinity, that's what this homogeneity 0 is telling us, are polynomials, and in this case the polynomial has to be of degree 0. It has to be a constant. Okay, so up to a numerical factor here, okay, we've got the answer. Even the numerical factor we can figure out by looking at the poles of the singularities. We know that the poles of the singularities have to come with coefficient 1. Okay, so there's some numerical factor which you can figure out. I'm not even going to try, but whatever it is, you can figure it out. It's determined. But notice that this answer that we derived for the fermions, we derived using only 3 things. We derived using the weights of the fermion operators. We derived using the zeros, the OP structure for e to the power h with the e to the power h, the zero, the psi with psi, the zeros, psi bar with psi bar, the zeros, and psi with psi bar, the singularities. But we've just checked that e to the power ih and e to the power minus ih have exactly the same properties in these 3 regards. They have the same scaling dimensions, same OP structure, and same zeros. So the same argument tells us that you're going to get the same answer, and in fact the same constant, because even the coefficient behind the singularities are the same. And so we found something quite marvelous. We found that the correlation functions of any correlation functions that you could write down with psi's and psi bars is the same as any correlation function you can write down with e to the power ih's and e to the power minus ih's. Now, there was this question about descendants, right? Since this is true, all the descendants will automatically work. So within this NS sector, all correlators of these theories are the same. So now this is sounding pretty impressive, right? Sounding very much like these 2 theories are the same or can be defined in such a way so that we make them the same. Okay, so already we've established something very interesting. The thing we've established is that within these NS, the correlation functions of these operators that we've studied are just identical, okay, between the fermionic side and the bosonic side. Okay, great. Any questions or comments about it?
One thing I was we would have chosen a field which is like exponential right to n plus 1 tensor, right?
We could have chosen more general operators, you're saying.
Yeah. So what
We're going to come to this. At the moment, we're just looking at what we get from here. Now, those operators that we could get by fusing 2 e to the power ih's are part of this structure, because we can take the OP between 2. Okay, so let's suppose I had e to the power ih of z1, e to the power ih of z2. Okay, in particular, you remember we saw this OP. This was z times e to the power 2 ih of z2 plus blah blah blah. So this operator, okay, its correlation functions will match with whatever the correlation functions of the first term from bringing 2 psi's together. Okay, but what was the first term when we brought 2 psi's together? It was psi del psi. Exactly. So the correlation functions of this guy will match with those of psi del psi, and so on. So anything that you can produce from OP in the NS sector will have a corresponding operator in the bosonic side just by doing the OPs. If you want to figure out the explicit map, work out the OPs. In fact, let's do this, since this question has come up. Let's do this to go far enough so that we get, if these two theories are the same, in particular they should have the same stress tensor. Meaning the stress tensor should map to each other. Okay, let's work that out as a sanity check. Okay. Okay, let's do that by taking psi of z, psi bar of 0, and going to a sufficiently high order in the OP expansion. You remember that after getting some things wrong, we figured out what the stress tensor was last time? I hope some of you have it in your notes, I'll never get the numbers right. Was it 1/4 psi del bar psi plus psi bar del, sorry, psi. Was T 1/4, was it half psi del bar psi bar plus psi bar del bar, so not del bar del. Was this right? Minus half. Thank you. Minus half. Okay. Okay. Fine. So let's go far enough in the OP so that we see this. Okay, so let's do this OP. This is 1/z plus normal order. First term in normal order is plus psi of 0, psi bar of 0, plus next term in normal order is z del psi bar of 0. Okay, did I do this completely right? Yeah, that sounds good. Maybe what I will want to do, I'm just wondering if I do a symmetrical expansion, because otherwise I'd have to do, because I want the other derivative as well. Let me do the symmetrical expansion. Okay. Forget it. Let's add. If we take psi bar of z, psi of 0. Okay, we get 1/z plus psi bar of 0, psi of 0, plus z del psi bar psi of 0. And therefore we see that psi of z, psi bar of 0, plus minus psi bar of z, psi of 0. Okay, this goes like, and maybe I'll take a half. This goes like 1/z plus, these are the same. Right? So psi of 0, psi bar of 0. Is this clear? Because we get psi of 0, psi bar of 0, minus psi bar of 0, psi of 0, but they're anti-commuting. No, I shouldn't have taken plus because then I will cancel things. I want plus, you're saying?
Yeah, if you add 1/z plus 1/z, right? If you subtract, it is 1/z minus 1/z.
Oh, why is it 1/z minus 1/z? These things are here. Subtraction. Thank you. Then maybe I don't want the 1/z. What I want is that these guys add up.
You want the 1/z. No, you want the anomaly.
1/z will be multiplying the whole expression.
1/z, no, will not be multiplying the whole expression. That's with the e to the pi h's. Yeah. I don't want the psi bar set size.
It will get cancelled if you add.
But I don't want it to cancel. Those are the things I want to keep.
So you want derivatives to keep, not the last term you
I want to match both this and this. Okay, but let me just do this minus. What do I get here? I get plus z del psi bar minus
So then 1/z will go away.
1/z will go away. Yes. Minus del psi bar psi. Now this is confused.
You want it plus, no?
I wanted plus to get stressed. Yeah, maybe you're right. Maybe I wanted the other one. Just give me a minute. What is this? I wanted this. It has to be clearly symmetrical. Okay, I think you're right. I think you're right. So that if I take plus, I will keep one term, 1 by z plus this. And I'll also work it out for minus, because I also want to compare the currents. Psi bar of z, psi of z, psi bar of 0, minus psi bar of z, psi of 0, goes like just order 1, psi of 0, psi bar of 0. Okay, this is on this side, fermion side. Okay, now let's work out the bosonic. Oh, anyway, this is not a nice classroom. Now let's work out the bosonic side. On the bosonic side, we had e to the power IH of z, e to the power I minus IH of 0. Let's first do this guy. Okay, so this was equal to 1 by z. This time we multiply over. Okay, into 1 plus I del h. Okay, now we have to do this a bit carefully, because we have this was e to the power I h of 0 plus z del h plus z squared del squared h by 2. And then when you Taylor expand this to second order, you get terms from here and terms from here. So we get I z, the whole thing squared, so minus z squared by 2 del h square plus I z squared by 2 del squared h. Right? Okay. And so we get, so this is plus del, this was z del h here. This was here? Main equation. Yeah. This was, but there was a 1 by z and then there was z del h, yes. And then there is minus z squared by 2 del h, the whole thing square, plus I z squared by 2 del squared h. Okay, so this was this guy, and then there was e to the power I minus IH of 0, e to the power IH of 0. Okay, so this is of course 1 by z into 1 minus I z del h, the whole thing square. And then when we expand to second order, there is, sorry, del h, thank you. When we expand to second order, this term continues to come with negative sign, because it was linear in the expansion, but this term will be positive sign, right? So I mean, yeah, so this will be the same sign, del h, the whole thing squared, minus I z squared by 2 del squared h. Now let's take sum and difference. Okay, if we take the sum, we get, so sum gives us 1 by z into 1 plus these cancel, 1 minus z squared by 2 del h square. A sum by 2, the average. And the difference diff by 2 is equal to 1 by z. No, 1 by z cancels. So yeah, so just this. So we get I del h, and then this other thing if we want to keep track of it, which will be plus I z squared by 2 del squared h. Z del squared h. Okay. Let me compare, to start with, the terms in the sum that were z squared. Okay. So in the sum, the terms that were z squared, z was del psi bar plus psi bar plus del psi bar psi. That was the coefficient of z there. But the coefficient of z here is minus del is the same thing as minus del h square by 2. That is the claim. Now, Rajat, right? Sorry, it told us that we got a half here. So the correspondence tells us that this is this with a 1 by 4. Minus half. So with a plus 1 by 4. Okay, and now we have to do some checking to see if we. It's clear that this is the same operator, right? The stress tensor for the free boson is del h squared. But was del h squared with some factor? Let's see if we've got. Have we been good enough to get the factor right? I very much doubt it, but okay, let's check. Give me a minute to. We'll have to do some detective work because Polchinski has the formula somewhere. It's impossible to find formulas. And then he'll have it in terms of alpha prime. But we'll manage. Or if you have it in your notes, even better, somebody.
It was minus 1 by alpha prime.
Right, minus 1 by alpha prime. Okay. Minus 1 by alpha prime. Are you sure this was half, Rajat? I have the feeling it's 1/4.
No, 1/4 for when you do t0. Then it becomes 1/4. Minus half time.
Give me 1 minute. Okay. We've got it up to a factor of 2. Let me just check the stress tensor. Yeah, you're right, it's half, or maybe minus half. Okay, can I leave this as an exercise for you to check the right factor of 2? I'm sorry about this.
H was normalized.
H was normalized. See, we should just get the right answer by just setting alpha prime equals 2.
But his stress tensor was in terms of x, not h.
Very good.
Doing for the right hand side and left hand side separately.
Is that right? Wait, what was the formula for the stress tensor? Somebody just, wait, was it minus half? Minus 1 by alpha prime del x? Yeah, so then if we just said alpha prime equals 2 and x equals h, when alpha prime equals 2, x is h. H is x at alpha prime equals 2. So we should have got half here. Okay, give me 1 minute. Let's see if I can. Why did we get the did we keep the in the fermion when I expanded? Oh no, that's okay. There's no factor of 2 there. That was okay. And
There should be a by 2 there, right? On the right hand side of psi bar and the symmetric sum.
should there?
Second term.
Well done. That's it. This should have been by 2.
That's Z by 2.
Yes, that's the by 2 there. Okay, so now the factor of half works. I hope it works the right way. Let's not look at it too hard. Okay, okay, fine. Okay, so you see how to do these things, right? Not only are these two theories the same, they're the same very explicitly. Any operator you wish to determine on one side, you can make in the NS, if it's an operator in the NS sector, you make it out of an OPE of size. All operators in the LS sector can be made out of OPEs of size. Then you do the same OPE on the bosonic side, and you'll find what the corresponding operator is with number, if you do it right. Right? Okay? So in particular, the two theories are the same, the stress tensors are the same. They're the same theory, more or less, except that we have not completely finished our work. Why have we not completely finished our work? Let's remember that the theory had operators which were PLI, PLH, e to the pi, PR, H, H bar, whatever, the right moving part of H. Okay? And you remember that we had this nice formula for PL. So PL was equal to N plus W by 2. Okay? Those guys that have any value of n and at least also potentially any integer value of w, even value of w, we can get from the OP of e to the power h with e to the power h. So e to the power 2ih or e to the power 3ih, so on, we can get. Okay? But if we have, let's say w equals 1 and n equals 0, that is a mode we will never get from OPEs of e to the power ih's. You'll never be able to produce half integer. Actually, let me say one more thing before we proceed. Although I didn't work it out, you can also check by looking at the minuses, you can also check the correspondence of the U1 charge currents. The guy that was psi bar psi on one side, up to some normalization, which I will not try to check, maps to del H on the other side. You can see that, probably see that from the formulas that are already still on the board. Okay, del H maps to psi bar psi. These are important operators because they generate the current for a U1 symmetry in the two theories. For the fermion, the current was just phasing of psi and anti-phasing of psi bar. For the boson, the current was more elementary. It was translation of the bosonic field. Okay? We've already seen this, right? That in the bosonic field, del X was the current for translations. Okay? And so U1 charge on the fermionic side, which was just number of psis minus number of psi bars, maps to momentum on the fermion side. The total momentum under your total charge under translations of X, of H. Okay? Great. So another way of saying this is that all operators that you get in the NS sector have integer values of U1 charge. Right? Because you have number of psis minus number of psi bars. That will be some integer. Anything that we get with integer PL and PR, let's look at the left moving sector, integer PL, will have integer value of momentum. But things that we get with non-integer PL, like W is equal to 1 and N is equal to 0, clearly have no analog with just size. Okay? So now let's study this operator. Okay, so now let's study this operator, the operator e to the power I h of z by 2. Okay. We're going to try to find out everything we can about this operator and translate it to fermion language. Okay? First thing we're going to find out is this. Suppose I take e to the power I h of z with e to the power I h of 0 by 2. What is the OP? What is the OP expansion of this thing? Okay? Now we just 5 minutes ago, 10 minutes ago did a very similar computation, except that there wasn't this by 2. Okay? But you know, the same rule, 2-point function exponentiate gets an extra factor of 2. So we'll get square root z. Is that clear? Okay, times normal ordered e to the power I h of z, e to the power I h of 0 by 2. Exactly, e to the power half log z. That extra factor of half made it square root z. Similarly, if we do e to the power minus I h of z, e to the power I h 0 by 2. Okay, this will be equal to 1 by square root z. Same reason. Okay, e to the power minus I h of z, e to the power I h 0 by 2. And then if we want to know more about what these operators are, we can Taylor expand them. Okay, so for instance, this guy at leading order will be e to the power 3h of 0 by 2. The other guy will be at leading order e to the power minus I h by 2, and so on. Okay. Now this is some mystery operator as far as the fermionic theory is concerned. Okay, I'm going to call it, no, this is special, there's a particular name, twisted spin, what a defect operator. Okay, we'll call it mystery operator. Okay, so this is the mystery operator from the fermion point of view. It's not built out of polynomials of size and psi bars. We want to investigate its properties. Disorder operator, defect operator, something, people, yeah. Okay. Okay. Let's call this operator, give it a name, let's call it O. Okay, okay. So this operator, this remember was psi. So this operator has the following feature. Psi of z with O of 0 gives you 1 by root z, root z. And psi bar of z with O of 0 gives 1 by root z. Okay. Now, because of this factor of root z, you see that if we put O at the origin and looked at the operator psi, it now is not single valued as you go around, but it comes back to itself with a minus sign. This is on the plane. What does that mean if we looked at it on the cylinder? You see, you remember that the transformation between psi on plane and psi of cylinder involved an extra factor of del w by del z to the power half, because the scaling dimension was half, which was a factor of root z. So half integer quantized on the plane becomes integer quantized on the cylinder. This is the same thing that we saw last class, that we looked at things that were half integer quantized on this. I hope I said that right. Half integer quantized on the plane becomes integer quantized on the cylinder. Same thing that we looked at last class. We started with half integer quantized on the cylinder. We found that the modes were integer quantized on the plane. Now it's reversed, because we've got half integer quantization on the plane, so it becomes integer quantized on the cylinder. Which means that what we're looking at are the dual to the Ramond sector states. Okay? NS sector was half integer quantized on cylinder and integer quantized on plane. This is Ramond. Okay? When we insert this, psi now becomes half integer quantized on plane and therefore integer quantized on cylinder. In fact, it is always true that if we take an h which is not just h of 0 by 2, but any alpha h where alpha is a half integer, the exact power will change, but the fact that we get a square root will not change, because it will be alpha times log z, and alpha is a half integer, is it, let's say 5.5, 5.5, we will get z to the 5 times square root z. Okay? So all the operators which have half integer momentum, all the operators which carry half integer momentum on the in e to the power ikx, they carry they have the periodicity that sets them belonging to the Ramond sector. Is this clear? Okay. So what we've discovered is that our bosonic theory, this mystery operator, was not just some irritant. Or the mystery sector, the sector of all momenta which are half integer quantized. It's not just some irritant, it was what we needed. We already knew we needed this in order to make the theory modular invariant. Okay? And the bosons are definitely modular invariant. How do we know it? We know because we checked. Right? So, okay, the bosons are pushing it towards modular invariance. And in doing so, they're introducing a new sector for the fermions. These are the Ramond sectors. Okay? Clear? Excellent. What? They are local operators.
If you are rotating around 0.
Excellent question. So, e to the power I h of z and e to the power half I h of 0 by 2 are not mutually local.
Yeah.
However, when we put left movers and right movers together, they are local.
Okay.
We checked it. Right? In the language of bosons, we checked that for every value of r, we got the phases from left movers and right movers cancelled. Do you remember? Okay? So we are dealing with local operators. The chiral algebra is not local. Left moving part is not local. The right moving part is not local. But the particular combination of left and right that we're considering gives us mutually local operators. In this part of our course, we're demanding that. Correlation functions that are not local in this part of the course are junk. When we grow up, we will learn to make peace with them. But at the moment, what is the answer? If a correlation function should be a number, shouldn't depend on how fast you move the operators, just where you insert it. So it has to be single valued. Is this clear?
How will these operators look in Ramond sector?
How will they look in terms of fermions?
Yeah.
That's an excellent question. They have no definition in terms of fermions. You see, if you want to think of them in terms of fermions, they're defined by this, let's say the ground state operator in the Ramond sector is defined by the following property. It's defined by the property that when you insert this operator, the OP of psi with that operator is square root z. And this turns out to be sufficient when you're clever enough to compute all correlation functions of these operators.
O with O's. All O with O's or
No, O with psi.
O with psi?
Okay, just the requirement that O with psi is a holomorphic function and that it starts at square root z. Okay, just that requirement turns out to be sufficient to compute all that, plus being clever gives you enough information to compute all its correlation functions. Also that, of course, with psi bar it's 1 over square root z. The arguments are a little similar to what I gave you about correlation functions of all psis with all psi bars. You fix the analytic structure, you see what happens at infinity, that determines the function. So you can make that argument quite cleanly. In fact, when we study orbifolds, we will have to make such arguments because sometimes in conformal field theories you get lucky, like we got here, but there's a dual description where there's a very explicit formula for these. There's a name, twist operators, something like that, twist operators. Okay, there's a very explicit formula for these twist operators. Okay, sometimes you're not so lucky. When we study Z2 orbifolds, as we will do soon, we will see we're not so lucky. We will have to deal with these operators abstractly. Okay, their holomorphicity properties and their correlation their local OP things are sufficient to determine all their correlation functions. So determine the operator, even though you don't have a formula for them.
So we don't have an explicit form of this.
Yeah, there's no polynomial form of this.
But we know the correlation.
But we know their correlation functions. In other words, we know the operator. Okay, so they're slightly more abstract things. They're defined by what their action is on the fields in the path integral. not by insertions of polynomials in the path integral. As I said at some point in this class, similar situation happens with monopole operators in 3 dimensions. Are you people familiar with this? Just give me 1 minute diversion. Suppose I have a U1 theory in 2 plus 1 dimensions. Let's say it's a conformal field theory. You somehow made a U1 conformal field theory in 2 plus 1 dimensions. Now there's a state operator map. Now the state operator map in that situation takes you from states on S2 to operators as we discussed in the early parts of this course. Now states on S2 in this U1 gauge theory come in sectors, because the flux on the sphere, the U1 gauge flux on the sphere is quantized in units of 2 pi, and so the flux can be 0, 2 pi, 4 pi, minus 8 pi, whatever. Okay? So the states in the theory in non-trivial flux sectors are some states, and the operators corresponding to these states are called monopole operators. Okay? And these operators are defined by the following requirement in the path integral. They're defined by the requirement that when you circle around the operator, when you make a little S2 around the operator, the flux measured in that S2 is the units of flux you have. And there's no better definition of these operators. These are the operators. Sometimes, now I said there's no better definition. I lied. For actually U1 gauge theory, you can use the duality between U1 gauge theories and compact bosons to make a more explicit definition, the winding sector things. But certainly in the SUN versions of these, there's no better definition of these theories, of these fluxes. Okay? Yet we are able to compute with them. They contribute to superpotentials, they contribute to all physical things. In ABJM theory, for instance, such operators join with the basic fields of the theory to make up SO8 invariance. Okay, they're very important things, and yet they're not. They're well defined deformations of the path integral that are local. That is all that a local operator is. Okay? So only in favorable situations that you can write them as a polynomial of the fields or an explicit function of the field. Sometimes you have to say that I'm going to do a path integral over all field configurations that have a particular kind of singularity at this point. That defines a local operator. Okay, so it's an excellent question, and without a satisfactory answer. Right? The answer is an abstract answer, but it's not a useless abstract answer. One that allows you to compute correlation functions. Is this clear? Yes.
Also, all this we have done is for alpha equal to 2. If we have some non-trivial alpha, it's not clear why there will be 2 sectors.
No. Alpha is not a parameter, right? Because alpha can be removed by redefinition of the field. Theories with different values of alpha are the same. Right? You just rescale. You've got 1 over 4 pi alpha prime times del x. Now let's say I take x to, square root alpha prime by 2h.
Okay, so my question is it's not clear why there are only 2 sectors, because you can have some other mystery operator O, psi z with O, which gives z to the power 1 by 3, let's say.
Z to the power 1 by 3. Excellent. But the problem with that is going to be the following. The stress tensor will not be single valued under the reason why half was allowed was that everything physical that you measure, okay, is a bilinear fermions. Now there's actually what? Bilinear because it's fermions. Fermions don't correspond to anything, but bilinears of fermions correspond to physical things like stress tensor, psi psi bar, or the U1 charge, current, whatever. Everything that you want, the Lagrangian is bilinear in fermions. Lagrangian has to be single valued. Okay, so however, I've given you an only partially accurate answer. The other thing that we could have done is have psi scale with weight alpha and psi bar scale with weight minus alpha, or psi scale with weight alpha plus half and psi bar scale with weight minus alpha. What is required is that psi bar is well defined, because stress tensor psi bar, Lagrangian psi bar, and so on. And those things you can make sense of. Okay? But those are define different theories. Okay, if you do this scaling, this defines a different theory, and it corresponds to deforming the boson side with what's called an improvement term in the stress tensor. So there is a little more you can do. That little more is whatever is consistent with keeping bilinears of psi and psi bar single valued. So it's treating psi and psi bar differently. If for a moment we want to treat the two fields democratically, psi and psi bar, there should be exchange invariance under psi and psi bar, there's nothing else you can. Is this clear? Okay, but all excellent questions. Please keep going. Okay?
These operators have charge half.
These operators have charge half under what? Under U1 charge?
Yeah.
Yes, they have charge half, as they should have had, because they're dual to e to the power half h, e to the power I h by 2. Okay? But okay, now let us understand a little more about these operators. Okay, let's understand a little more about these operators. First, let's compute their scaling dimension. Okay, that's really easy, because we had a formula for scaling dimension. It was PL squared by 2. L0 is PL squared by 2. But PL is half. So we get that H of O, HO, is equal to 1 by 8. Is this clear? So it's an operator of dimension 1 by 8. Okay, it's an operator of dimension 1 by 8, and this is going to be the ground state operator in the Ramond sector. Okay, fine. Now, let us try to see that this thing is really working. I'm claiming that this operator is actually one of the two ground state operators in the Ramond sector, because there's e to the power I, there's the operator which was e to the power I h by 2, and there's e to the power minus I h by 2. You know, if you just flip the role of psi and psi bar, you would get the other operator. So in fact, this Ramond sector has two twist operators, one of charge half, one of charge minus half. Okay, and I'm claiming that these two are the ground states in the Ramond sector. So what does that statement even mean? Why are there two ground states in the Ramond sector? Okay, so let's try to do an independent fermionic calculation. Okay, the independent fermionic calculation that we're going to try to do is to understand the vacuum, the spectrum, and in particular the energy of the vacuum in the Ramond sector. Okay, so let's see. So what we have is a bunch of fermionic harmonic oscillators. Okay, a bunch of fermionic harmonic oscillators of integer dimension. Of integer, yeah.
Does the ground state have non-trivial scaling dimension? Because otherwise, I mean, if you just compute the scaling dimension using the correlation function, x0 is like O0 has dimension 1 by 8.
Yes.
But they should add up to half. They should add up to half because yeah, I mean, no, I'm confused. Psi of z has dimension half.
Psi of z has dimension half.
O0 you're claiming that it has dimension
1 by 8.
Sure. So there should be some calculation there.
Between what and what?
Because on the right hand side it should be square root of z.
There is e to the I also.
What? On the right hand side it should be square. You see, these scaling dimensions are consistent with the OP, if that's what you're worried about.
Yeah.
Let's check that. The fact that it worked here, let's look at one of these guys. Let's say that we have e to the power I h of z times e to the power I h of 0 by 2 goes like square root z times the first operator, as we saw, was e to the power I 3h by 2 of 0. This is the claim. Let's try to understand how that works. Okay, how does this work with dimensions? This guy had dimension 1 by 8. This guy has dimension half. So the total dimension on the left hand side is half plus 1 by 8, which is 5 by 8. 5 by 8. Now let's look on the right hand side. This guy has dimension minus half because it's square root z. What about this guy? This guy has dimension 3 by 2, the whole thing square. So 3 by 2, the whole thing square by 2. So 9 by 8. And it should be a magnificent fact of mathematics that 9 by 8 minus half is 5 by 8, which is true. Okay? Another thing you may be concerned about is what was this 9 by 8 on the fermionic side? But notice that 9 by 8 is 1 by 8 plus 1. Okay? So it's just, it has what it takes to be, and also it has charge 3 by 2. So it will be size, it will be a, what could it be? Let's see. It has to have charge 3 by 2. Yeah, so it will be psi times O. You know, the first term in the OP, wherever you take psi with O, I mean, of course, that's what we're saying, right? Take psi with O, do the OP, there's a term which is square root z, whatever that thing multiplies is this operator. You can call this operator O psi if you want. Okay, O psi, this is a new operator, but it has dimension 9 by 8. Certainly it's charge 3 by 2, as you would expect. Okay, fine. Okay, great. Great. Did I, you know, there's no, this is a new sector. The consistency condition perhaps that you want is the one I'm going to do now. That is, there should be a way of checking directly from the fermion that the dimensions are working out right. Okay, and I'm going to try to do that check now. Okay. By the way, before doing that check, I told you that these guys were the ground states. Let me check that using contour methods. Remember that we took our psi and we expanded it as sum over m alpha m z to the power m plus half. In the NS sector, this m ran over, in the NS sector, the m ran over half integers. Now m runs over integers. We have a similar expansion for psi bar. Alpha bar m z to the power m plus half. Okay? What I want to do is to figure out what in the Ramond sector, what I can say about the operator O, where this O was this mystery operator. Okay? O was e to the power I h by 2. What it is in Hilbert space language. Okay, question clear?
What is the state corresponding to?
What is the state corresponding to it? The state, we know what the states are on the cylinder, right? Because we just quantize periodically. So we've got harmonic oscillators, which are creation and annihilation. We just want to figure out what it is. Okay? That's an easy calculation to do because now we've become experts at these calculations. So let's do the calculation. The computation goes this way. We want integral, we have alpha m is equal to 1 by 2 pi I times integral z to the power m minus half psi of z. Right? And we want to act this contour. What I'm doing is what we've always done. I'm going to try to figure out what alpha m on the state O is. But that is the same as acting this contour on the operator insertion O. That's clear, right? And we know what we're going to get, right? We've done this a zillion times now. We're going to get we're going to get what you get from the OP, from the pole, the residue of the pole in the OP between whatever was here and O. Okay, so we're going to get the residue of the pole from z to the power m minus half times square root of z times dot dot dot. Okay? Is this clear? We're going to have to pick out the residue from here. First, which ones give us 0? Okay, so if this square root of z is cancelling this half, so for m greater than equal to 0, we get 0. Right? Suppose I did the same computation for alpha bar of m on 0. Or no. The only difference here is that instead of this square root, we get a 1 by square root. So can you say that for the answer is m greater than equal to 1, we get 0? So we have this is equal to 0 for m greater than equal to 1, greater than equal to 0, and this is equal to 0 for m greater than equal to 1. Now, remember, positive m's were annihilation operators. Negative m's were creation operators. Okay? With this information in mind, can you tell me what the state is? It's an unfair question because it involves. Let me say a little bit more. You see, something that I'm doing this calculation partly for this reason. To remind you that the spectrum in the Ramond sector is a bit different from the spectrum, even qualitatively, from the spectrum in the NS sector. Spectrum in the NS sector was a bunch of harmonic oscillators. Okay? Spectrum in the NS sector was a bunch of harmonic oscillators. And the correlation functions went like this. We had commutation relations went like this. Alpha bar m, alpha n to delta mn. These m's and n's ran over all integers. So for any value, absolute integer, let's say 5, there are two creation and annihilation operator sets. Because there's alpha bar 5 with alpha minus 5, and there's alpha bar, I'll write it down. Say we are at 5, there is alpha 5, give the alpha bar minus 5 is equal to 1, but there's also alpha minus 5 with alpha bar 5 equals 1. Right? So at any given integer, there are two fermionic harmonic oscillators, two creation annihilation operators. Right? So because there were two psis, there was a psi and a psi bar. This is true for every integer except 0.
Because there it started from half.
Half.
M and n were half.
That was in the NS sector. Now we're in the Ramond sector. Ramond sector, because last time we were in the NS sector, we never had to encounter this issue. Every half integer appeared twice. But integer, there's one integer such that minus of that integer is the same integer, namely 0. So these two are the same. We only have one harmonic oscillator with 0. Alpha 0, anti-commutator alpha bar 0 is 1. So at 0, we don't have two harmonic oscillators. At frequency 0, we have one harmonic oscillator. Now, what is the energy of this harmonic oscillator? Omega of this harmonic oscillator. Come on. 0, right? The omega is n. The L0 of this harmonic oscillator, the weight, is n, right? Or minus n. It carries positive energy if you have minus, right, and negative energy if plus. When you have 0, the L0 value is 0. So we've got a two-state system in the Ramond sector, which carries 0 energy. Built on top of this two-state system, there are a bunch of harmonic oscillators, two harmonic oscillators for every energy. But the vacuum itself has two states. Okay. So the vacuum itself has two states. The states that are annihilated by all annihilation operators for positive frequencies. But do what they do in this two-state sector. So now that with that, look at that box and tell me what state we had.
Alpha 0, alpha 1.
Right. Excellent. So firstly, it's the vacuum, because it's annihilated by all annihilation operators with positive frequencies. And then this two-state system for the vacuum can be represented as up and down with some convention. Let us say down is annihilated by alpha. Let's say that alpha 0 on down is equal to 0, alpha 0 on up is equal to down, and the reverse for alpha bar. You can easily check that that implements this commutation relation. Okay? So with this convention, alpha 0 was annihilating the state, but alpha bar was not. Shouldn't, right? Because alpha bar on down will give you up. It won't annihilate it. Alpha bar 0. So this was the state down. Whereas if we worked with O bar, e to the power minus IH by 2, we would have got the state up. Is this clear? Okay? So this was the state that we were dealing with under state operator map. Okay? And the fact that we got 9 by 8 for the scaling dimension for the next guy will be basically that that state in the Ramond sector, that e to the power 9 by 8 guy, will be alpha minus 1 acting on vacuum. Because alpha minus 1 carries L0 equals 1. So it increases the L0 value by 1, but the vacuum at 1/8. So this state will have 9/8. So the state, that operator that we got, this operator which was psi O, was the operator dual to the state alpha minus 1 on vacuum. So e to the power 3 e to the power I 3 by 2 h is that operator in fermionic language is dual to the state alpha minus 1 acting on vacuum. Please go ahead. Yes.
When you write the psi as the scalar series, you actually mean psi O, right?
Where did I write psi?
Psi is alpha m by z m to the power.
Yeah. So this, you say, I'm looking at what's happening with psi in correlation functions that have an O in the middle, O at the origin. In any such correlation function, this will be the expansion. Okay? In the absence, psi would have the same kind of expansion, but with half integers.
So this can be looked at like psi O at z.
It's how psi is behaving in a path integral which has an O insertion. Okay? Excellent. Okay. Now we were going to do a calculation, but we also have to eat lunch. I'm just wondering how long this calculation will take. It all depends on how many mistakes we make. Let's do it next time. We'll do it. I wanted to show you that the ground state, that the energy of the ground state is actually 1 by 8. Okay? And the way I'm going to do it, in fact, you can try to do it yourself. Try to do it yourself and we'll check. It'll be good. If you try it yourself, then you can correct me while I'm making my mistakes in class. Okay, so I'll tell you the method. The method that we're going to use is this. We'll compute the Casimir energy, both in the NS sector, we didn't even do that. Okay, and in the Ramond sector for fermions. You remember we did this for bosons. And we added 1 plus 2 plus 3 plus 4 and we found that was minus 1 by 12. Yeah. So we're going to have to do something similar here. Okay. That computation should somehow allow you to predict this 1 by 8. Try to think this through. In fact, if you want to do it, we first do it in the NS sector. In the NS sector, you will have to do the calculation, half plus 3 halves plus 5 halves, and so on. You will find minus 1 by something, whatever. So you'll find something. Match that. How does that minus 1 by 12, if you remember, we had an interpretation for? Can somebody tell me what was the interpretation? How we got this Casimir energy, but there was another way of getting that. What? Louder? Curvature thing. Related. But you remember that the ground state was the state corresponding to the operator identity. So you might have thought that Ground state energy should match the dimension of the operator identity, which was 0. So why did we get minus 1 by 12? This Schwarzian business, right? So dimensions on the plane match energies on the cylinder up to a shift by the Schwarzian. So up to a shift by C by 12. Dimensions, energies on the cylinder lower than dimensions on the on the sphere or the plane by C by 12, or L0 is lower by C by 24. Okay? So now that we have this, can you predict what you should get when we do for the fermions? What should we get? In the NS sector, what should we get? 1 by 24, because this was a C equals 1 theory, because there's psi and psi bar. Yeah, so for L0, we should get the same as for bosons, 1 by 24. Okay? So first thing you can do is, for one of, we've got two fermionic oscillators. So that tells you for each fermionic oscillator, you do the half by 3 plus 3 halves plus 5 halves, you should get minus 1 by 48. So that 2 times that is minus 1 by 24. Try to check that. Next, how will we get this 1 by 8? Okay? What we're going to we'll get something from a Casimir energy computation. And then to go to the sphere, or to the plane, to get the scaling dimension from that, we have to add C by 24, which is 1 by 24. So the answer we get plus 1 by 24 should be equal to 1 by 8. Okay, so the answer we get should be 1 by 8 minus 1 by 24, which is 3 by 24 minus 1 by 24, 2 by 24 by 1 by 12. We should get the answer 1 by 12. Okay, check that you get that. That's the calculation I was planning to do now, but I suspect we will get stuck in. Let's do it together next time.